This video is based on measures of central tendency, more commonly known as mean, median, and mode. So let's talk about the first one, mean. Mean is essentially the average of a data set. Now we have two different types of symbolic representation, and we'll be using both of these later, so that is important. For the population mean, meaning it's the average of a population set of data, we use the Greek letter that is called mu. It's kind of a weird looking U with an extra tail on the left. It looks like you can't decide whether it's a mu or an M. I mean a U or an M, excuse me. But the way you calculate that's pretty straightforward. We've talked about that symbol right there. That's another Greek letter, sigma. You don't have to know that that's sigma. Just realize that that is the symbol that means summation, meaning you're going to add stuff up. And X just represents each individual data value. Like your first number would be X1, the next one's X2. So essentially, and then capital N is population size. So what this means is just you add, like you would normally compute an average. You add up the number of values you have, and then you divide by how many values there were. This is just a symbolic way to properly write it. Now for sample mean, we don't use a Greek letter, we use an X with a little line above it. We literally call that X bar. Remember, a sample is essentially a subset from the population. That's one of the definitions off of my sheet of statistical terms and definitions. But it's calculated the same exact way, but the notation is different because there are times where both of those are going to be used and we need to know which is which. And so you add up your data values and you essentially divide by how many of them you have. So the mean's real straightforward, real easy to calculate. So here's an example where I said find the sample mean for this set of data, 12, 8, 3, 7, and 6. You can just add them up. So I just used X bar only because of the wording saying sample mean. X bar, add them up, 12 plus 8 plus 3 plus 7 plus 6, divide by 5, equals 7.2. That's all you got to do. Now the next one I gave a set of data, but we called it a population. So the only difference is I used the Greek letter mu, added the 5 numbers up, divided by 5, and got 8.8. So I think calculating the mean is pretty straightforward and easy enough. Now we have something called median, which is the middle value of an ordered data set. Very important that it must be ordered from lowest to highest, because what you're saying about the median is you're saying it is a value where 50% or half of your data values are smaller than that number and half are larger. So they must be sorted. You can't just visually look at it. Now for mean, obviously the order doesn't matter. You're just adding up those values. So let's say you took these numbers right here, 12, 8, 3, 7, and 6, and you just said, hey, I'll pick the one in the middle. That's 3. Hooray, I'm done. Well, that wouldn't be a very good answer. You could get lucky in some situations, but we don't want to do that. Then you're saying out of those 5 numbers, 2 of them are less than 3 and 2 of them are greater than 3. That's obviously not correct, is it? They're all greater than 3. So you resort them, 3, 6, 7, 8, 12, and then 7 is your median. Okay, now here's another one. Resort them, and then you'll see that 9 is your median value. Now these first 2 examples, we had 5 numbers in the first one, we had 9 in this one. Whenever you have an odd number of values, there will always be one precise number that you mean. But when there's an even number of values, you have to handle it differently, because you won't have one unique number. When you have an even number of values, just sort them as normal, but you won't have one single number. You have to find the middle 2 values. you have to average the middle two, and then that will be your median. So, it's very possible that the median will not be a number in your list whenever you have an even number of values. And your odd number of values, it will always be in your list. So in this case, we find 9 and 11 in the middle. We add those together, divide by 2, and we get 10. So 10 would be the median of that data set. That kind of makes sense if you think about it. You put 10 right in the middle between those two. 5 of them are less than 10. 5 of them are greater than 10. Now, I'll show you how to do this on the calculator real quick if you have a TI type calculator. Now, I'll just mention real quick for this, I did this problem right up here. When you put them in the calculator, by the way, they don't have to be sorted. You can put them in whatever order and the calculator will sort it. Well, what you don't see here, if you look at the end of these values here, 1, 17, 6, 15, 11, 18. That just shows here, but above that 1 are the other numbers. In fact, you see this L111 means that where that black bar is, that means it's waiting for an 11th number. That means it knows there's 10 numbers above it. So the 6 that are there plus the 4 you can't see. But I can really just make up any example to show you for this. It doesn't really, I could even take anything. It doesn't have to be that one, but that would be a good one for you to try if you wanted to. So you go to Stat. This is a little bit newer operating system of the TI, but it should work pretty much the same way. And, if you're not sure, there are a lot of YouTube calculator videos, so you can always YouTube videos that are specifically for a type of calculation you're looking to do. So I'm going to do, I don't know, I'll do 1, 2, 3, 4, 5, 6. Now this one shows more numbers than the other version too. So 1, 2, 3, 4, 5, 6 would actually have a median of 3.5 because you would take the 3 and the 4 and you would average them together. But now I'm going to put them in a variety of orders, like I was saying about not being in order. 6, 4, 1, 5, 3, 2. All right. See, so there they are, 1, 2, 3, 4, 5, 6, just not in order. So you go second, quit, then you go to Stat, Calc, 1var stats. Now yours will show 1var stats, and all you have to, if it shows a 1var stat blinking, just hit enter. I don't think I have to hit anything here. As long as my data is in L1 every time, you're okay. Okay, I have to scroll down to get to the median though. There it is. I'm going to scroll down a little further. We'll be using all those numbers later, but you see how the median's 3.5? There it is, 3.5. So it did not have to be done in order. One more thing I want to show you before I go back there is, I'm going to quit out of this, or I could have cleared it. But anytime you want to get rid of data that's in a list, you can type over it obviously, but let's say you're going to put fewer numbers in that were already there. To clear a list, if you arrow up to where the list is, like L1, and you hit clear, nothing looks like it happens. But as soon as you move an arrow, I know down, maybe the other directions, but I know for sure if you move the down arrow, then it empties out the list. It's kind of strange that it doesn't clear it when you hit list immediately, but you move that arrow, they're gone. But if you're using a TI 83 or 84, you'll go to 1var stats, hit enter, and it'll have one thing flashing next to it. That means it wants to know what list you're talking about. L1 is the default list, so that you don't have to do anything. That's why I just put your data in L1 every time, and then hit enter, and then it'll spit out what you need. But like I said before, nothing wrong with checking a YouTube video there if I went too fast on that. So, but anyway, there's that median 10 that we did right up here. So it did do it correctly for that one right there. Now here's just an example. Median is, obviously mean is very commonly used, but median is very commonly used data set. I've seen median salary, median home price, things like that. And I just kind of use an example here. Let's say if a professor was given an exam and the mean was 78, but the median was 84, meaning half the score is below 84, half is above 84. If the mean is significantly lower than the median like that, that means that there were just some kind of really low scores that kind of drug down the average, but it didn't affect the median. And that's something to think about too, is if the professor's trying to establish how hard was the exam. I don't think, if you had people making 5s and 10s on the test that had a median of 84, that just means they were unprepared for that exam. That's not necessarily a reflection on how difficult your exam was. A median of 84 would say, hey, half the people made better than 84. So this just eliminates us worrying about what the scores were below 84. We just know that half of them were below 84. Now here's a very important statement right here in red. The median, we're going to learn, and some other statistical measures. I'll probably say this again in the next video. But the median is the only one of the between the mean that we've learned and what we're going to learn that's unaffected by outliers. Meaning that, remember, outliers we just kind of talked about, generally numbers that are kind of far away from the average. So like this one, these 10 and 20 would kind of be outliers. This has a median of 80 and a mean of 600. So in other words, if you were to change any data value significantly outside of the median, you would affect the mean greatly, but you would not affect the median. For example, suppose you had the data set 1, 2, 3, 4, 5. The median would clearly be 3. But suppose then you had a different data set, 1, 2, 3, 4, and then 500. Well, that wouldn't affect the mean. The median would still be 3. But the mean would be drastically affected by that 500 value. It would skew the average. So the median, though, is not affected by outliers. It's just what's in the middle of the list. The mean would be. So once you hear, I'm just actually writing out outlier. I did not in the last video. I just kind of said what it was. But here it is, far removed, low end, high end, just anywhere that's kind of out of bounds. Like I said, there's a way we can check it later. I can sort of show you. I never generally ask you on a test to define whether or not as a point is an outlier, but it's important to understand the concept. That's the main thing. I would consider 35 to be an outlier. It's kind of close, though. It's not as obvious as like 300 would be or whatever, but so let's look at this list of 8 numbers. So the median would be 8.5. I'm sorry, 7.5, because you sort the middle two, 7 and 8, sort them and average the middle two. 7 and 8 make 7.5, and the average is 10. That 35 had an effect on the average. The next topic is mode. Mode is a data entry that occurs the most number of times, provided it occurs at least twice in your data set. So it has to be something that occurs at least twice. Oftentimes people they confuse this, that if it occurs more than twice, it automatically is the mode. No, it just has to occur 2 times or more to have a chance to be the mode, but you're still looking for the one that occurs the most number of times. Now you can have a tie, which I'll show you an example where you'll see the third one here. Well, let's look at this right here. These 6 numbers, they're all different numbers, no repeats. That data set then has no mode. The next data set. Now, if you notice, there's 2 1s and there's 2 6s. That means 1 and 6 can be considered for being the mode because they occur more than once. However, look at the 7s. there are 4 7s. So it is the winner of the mode since it occurs the most number of times. But the 1 and 6 were eligible, but 7 was the ultimate winner here. Oh, got away from me there. Let's see. The next example, there are 3 4s, there are 3 5s. Nothing occurs more than 3 times. Therefore, we would say modes, plural. This would be a legitimate tie for mode right here. Modes, plural, of 4 and 5. Now, mode is the only one of these 3 measures, mean, median, and mode, that applies to qualitative data. In other words, you can have qualitative data as your mode. It does not have to be numerical data. That would not be true for mean and median. Mean, you can't, like for that car example, you couldn't exactly average the number of cars you prefer, that sort of thing. Let's see. Let me bring that back up here for a second. I believe that was... yeah, this example right here. Let me change this in the notes where it said 2.1. It should have said 2.2. Okay. We would say, from that example back here in this section 2.2 of that data set, we would say Honda was the mode because it occurred with the largest number of frequencies. So yes, you can have word answers for your mode. Now let's look at what's called different shapes of distributions. We'll look at continuous data later. We haven't learned about that yet. Sometimes data doesn't have to be separated by bars. It can be continuous like that. But that's more likely now you'll see it in bar histogram type form. Or actually, you can determine this from stem and leaf. It doesn't have to be presented like this. Dot plots would accomplish the same thing. You could look at a dot plot. So it's not just bar graphs. But we call a data set skewed right if it has more data on the left, the lower ends, whether that was dot plot or the only difference between stem and leaf is stem and leaf would just be sideways, but you would still see the top of the stem and leaf would be lower end. So, so this might seem backwards to what you would think the answer is, but you just sort of have to accept it and go with that's the way it's defined. So heavier data, more on the left, skewed right, and then just the opposite here when you have more data on the higher end here than you do the lower end, that's called skewed left. So we just sort of have to accept that naming. Uniform. Now, perfectly uniform would be if all the bar heights were exactly the same, but we can use the term uniform to also represent if they're close to being the same, roughly about the same height. So I think this is sufficient to say this data set is uniform. It's not perfectly uniform, but they're all close. It's certainly not skewed. Now we look at what's called symmetric, but not uniform. In other words, all uniforms are symmetric, but not all symmetrics are uniform. So we're looking at non-uniform symmetric. Because the idea behind symmetric is if you just take the middle and you fold it across the middle, it's the same or roughly the same, close to being the same on the other side. So you see, any uniform would be symmetric, but we keep uniform as its own category. So like, see, you took this middle bar, folded it over, it would be the same on both sides. And here they are in curve. We're going to be studying this bell curve a lot in this class later on. Here's another one, so you put it right in the middle and it would fold over. That data actually has a term called bimodal. That would be an example of 2 modes. Now here's just an example. I guess you can pretend like that answer is not there, although you could see it. What shape would you classify for the distribution on the right? And I'll see. It's heavier on the right, therefore that is skewed left. Now, there are special types of means. Sometimes in a data set, we don't consider all values to be equal, like we did just for our generic definition of mean, where you add them up and divide by the number of values you have. The most common example that I think that would relate to students as far as weighted mean would be if you were taking some sort of course where each different components of the grade have different percentages associated with them. That's the idea of weights. They all have different weights. Some scores are more important than other scores. So here's an example of, made one up. I said, suppose you're taking a course where 15% is homework, 15% is quiz, you got a 10% computer lab, you got a 30% midterm, and a 30% final. Now here's the formula for this, and you multiply the X, meaning each score that corresponds for each category, multiplied by the weight. So it's the score times the weight, add those up, divided by the sum of the weights. Now for this example, the sum of the weights is always going to be 1 because of 100%. But there are, I'll show you another kind of example where that's not the case. So we have, so I just made up 5 scores, and just they go in order exactly matching up here. So let's say we had those 5 scores: 92 on homework, 80 on quizzes, 100 in the computer lab, 75 on midterm, 76 on the final. What is your course average? Sometimes, I like to put these in chart form, but you don't really need to do that by any means. It's not necessary. That may help you organize it better. So all you really have to do then is take 92 homework, multiply it by 15%. So here it is over here. 92 times 0.15. Then we have 80 times 0.15. Then 100 for the computer lab times 0.10. 75 times 30, 75 times 0.3. And then 76 times 0.3. So you add those up, and then we'll divide by the sum of the weights, which is 1 for 100%. That's where that 1 comes from. Now, it's up to you whether, if you're the kind of person that wants to multiply each of those, write them down, then add them up, that's fine. But ultimately we just need the total. That's what each XW product is not important by itself. It's just important because it makes the total. So you see, I did it all in one string there in the calculator, just one step. 92 times 0.15 plus 80 times 0.15 plus, so forth, so on. But if you prefer not to do it that way, that's fine. I simply like writing down every individual number, and that came out to be 81.1. And divide by 1, so your course average was 81.1. So I guess we squeaked out the B's. Then I just threw a hypothetical in there and said, all right, what if we didn't have the weighted average and your course grade was just based on those 5 scores, all equally weighted? In that case, if they're all equally weighted, you just add them up and divide by 5. So it's not really a weighted average anymore. And it would have been 84.6 if that was the case. They were equally weighted. Now here's an interesting problem that's often I get asked or whatever, and it's not that difficult to figure out yourself as a student. The typical, what do I need on the final to make a certain average in the class? That's not really difficult to calculate. It's a very, very basic algebra type problem. So unlike the last one, I'm using the same percentages. It looks like I'm using different scores. No, I'm using the same scores, just not with the finals unknown. So what we do here is, and instead of this case, though, the last example, you see where I have the box above that X, that was a 76, and then we calculated the total. So the only difference is this time I'm writing them out as individual products, so we kind of need to for this one. Where X times 0.3, meaning the final is 30%. So X times 0.3, So this time we don't know there. The unknown is here, but then we know the total, average of 80. Of course, that means 80 or more. So we're looking at the minimum score we need to get an 80. So obviously anything higher than that's good too. Now, there's a slight mistake here I need to fix. Okay. I believe the calculation is still correct. I'll check, but just wrote an extra 7 there. So the 58.3 represents everything, the first 4 terms multiplied and added together is 58.3. And then you have the 0.3x and then 80 on the other side. So pretty simple algebra to subtract 58.3 on both sides. You get 21.7 and then just divide by the coefficient. So 21.7 divided by 0.3 is 72.33. Okay, you may not be able to get an actual 72.33 on the test, but that kind of gives you a ballpark figure. Then you know you could say 73 for sure would do it. If the professor uses a sort of a rounding like 79.5, 72 is probably good enough. But yeah, but that's basically the idea. That would kind of ballpark it for you. I'm gonna check this out. 21 divided by 0.3. Yeah, for some reason I had an extra 7 written there, but I had the calculation done correctly. So I like the ones calculating the course average. Those are good ones I like to put on tests. Here's another example of one that I've never actually put on a test, but I thought I would show you real quick. It's a weighted average, but the denominator this time is not 1 like it is for the percentages. If you ever wanted to calculate a GPA for whatever reason, you're basically looking at number of grade points divided by number of hours attempted. So the hours are the weights and the X values are the grade points. Or you could argue reverse it if you wanted to. Anyway, that's not critical. So an A is worth 4, B is worth 3, C is worth 2, D is 1, F 0. So if you made an A in a 3-hour class, 3 times 4 would be 12. A C in a 3-hour class, 3 times 2 is 6. B, 3 times 3 is 9. A is 4, 3 times 4 is 12. Add those up, get 39. And then you take 39 total grade points divided by 12 hours attempted. So that means that GPA for those courses would be 3.25. Now the last type of mean here is called mean of a frequency distribution. And this is actually, I call this what I say a crude approximation of the actual mean. Because in this situation, you are not given the list of all the data values. If you had a list of the data values, all you would then need to do is add them up and divide by how many of them you had. You would just calculate the mean as normal. So all you were given in a problem like this is these first 2 columns. You're given the intervals and you're given the frequency. So all you know from this data, all you know is that between 63 and 65 we have 3 numbers. 66 to 68 is 6, so forth, so on. And we do know there's 23 total numbers by adding up the frequencies. So you're only given these 2 columns. You're not given this midpoint. The midpoint, I'll show you in a second how to calculate. One thing I like to ask at this point when I'm teaching a face-to-face class is just as a review, look at these intervals and what would the class width be for that? That's a good practice. Class width be. I'll pause for a second before I answer to give you a chance to think about it. So the class width of this would be 3. It would be 3, not 2. It's measured vertically, not horizontally. So it's measured down. So 63 to 66, 66 to 69, so forth, so on. It's a class width of 3. Now the midpoint, the class midpoint is very easy to get. You just add the 2 ends of the intervals together, the lower limit, the upper limit, add them together, divide by 2. So 63 plus 65 divided by 2 is 64. Now, here's a quick way you can get the rest of them. You don't trust yourself to do it this way. Go right ahead and add them, divide by 2. No problem. But if you know that you see that the class width is 3, that the lower limit's going up by 3, the upper limit's going up by 3, that means the midpoint will go up by 3. Of course, it's very important you get the first midpoint correct. So then without having to average all the other ones, if you know the first one's 64, the next one has to go up by 3, 67, then you go up by 3. So here's what the formula is for this one, except x is different here than what it was for the weighted mean. X is actually the midpoint value. And of course, F is still F for frequency. So you're multiplying, now of course, I have F then X. The order for multiplication doesn't matter. In other words, F times X, X times F, same thing. So you're multiplying each frequency times the midpoint, frequency, midpoint, so forth, so on. Now the reason why we're using this midpoint is, since we don't know how many the values in there's 3 of them. There could be 2 63s and a 65. There could all 3 be 65s. We don't know. So we're sort of taking a conservative estimate here. We're basically treating this as if it was 3 64s right in the middle. So that's what I mean. That's why this is an approximation of the real mean. So it's kind of the safest estimate you can take by picking the value in the middle. So that's all this is doing. So it's like we're saying there's 3 64s, 6 67, so forth, so on. So you take the all these. Once again, you don't need the individual values, but if you'd rather build another column and do 3 times 64, write that down. 6 times 67, write that down. Then add them up. That's fine. But once again, I just did them in one step. I went 64 times 3, 67 times 6, 70 times 7, 73 times 4, and then 76 and 3. And I did them all in one step in the calculator and got 1604. And then divide by the total number of frequencies, which is 23. So you get 69.74. Once again, the rounding is not important. You're just picking the right answer on a test. So, I mean, the exam may only have 1 decimal place. I would expect 1 for sure, but I went ahead and put 2 just in case. Now, one thing very important when you make these calculations is this answer did not have to end up in the middle. It kind of did because the data is symmetric is why it did for here, but it's got to end up somewhere between 63 and 77, because if you're averaging numbers that are between 63 and 77, even though we're using midpoints, you're not going to get an answer outside of the range 63 to 77. So just make sure your answer there fits somewhere in there. Okay. Now here's another example. We'll just look at this one real quick. So sometimes if the only difference between here, here's the frequencies. The midpoint might be a decimal point if it was specifically 0.5. That means if your 2 numbers add up together to be odd, and when you divide by 2, that leaves you a 0.5. So don't round that or anything. In other words, 60 plus 69 is 129 divided by 2 is 64.5. Use the 0.5. So you see this one, the class width is 10 measured vertically. Goes up by 10, goes up by 10, so you can go up by 10 there to save yourself some time. Now I left these blank, meaning that if you like to put the individual numbers in there after you multiply those 2 columns, you can, but mainly all you need is the grand total, which is what I did right here. So you see I just strung all up in one sequence again. Multiply, add, so forth, so on, and got 3423.5. Divide by 43. And so you might see I mentioned again, you don't have to show each individual XF product there. And I got 79.62, which is in my range of values there, so that's a good sign. Now we're not going to worry about, we are going to cover something called variance and standard deviation of a regular data set, but we're not going to do it for this. That'll be in the next section. And it looks like I just kind of added another example there. Nothing new in this technique right here. Same thing. You see the midpoints. We just happen to be 0.5s here. Multiply, multiply, multiply. Add them up. This one's 702. divided by 36 total frequencies, we get 19.5. That falls in here. So I just kind of put another example in there. Same idea. All right, so try that out. I think once you can do that successfully one time, you should be okay. So that ends this particular lecture.